Okay, hello everybody. Welcome to our 12th VPEC webinar. The webinar title today is Advanced Power Converter. First, I would like to introduce myself. My name is Min Khai Nguyen. Now I work in West State University in USA. I will be a chair in this webinar today. And I would like to introduce my co-chair, Dr. Anh Dũng Nguyen from Virginia Tech, United States. Today we have two speakers. The first one that's Mr. Oscar, and the second one, Dr. Thanh Hải Nguyen. Each speaker had 1 hour, includes 40 minutes presentation, and we had 20 minutes for question and answer. Right now, I would like to introduce my co-chair, Dr. Anh Dũng, a little bit introduce about you.
Okay, thank you for your introduction. My name is Anh Dũng Nguyen. I got my PhD degree from Taiwan Tech, Taiwan, and then I moved to the Virginia Tech for the postdoc associate under position line. And my research interests include the magnetic design for the power converter and high efficiency, high power density power converter. Yeah, that's it, and nice to meet all of you. And yeah, welcome to the 12th webinar. Thank you.
Now we move to the first presentation. The first presentation from Oscar. Oscar received his bachelor degree in electrical engineering at the University of Texas in Austin. He currently working as a leader hardware engineer with the research interest power converter, inverter, and renewable energy application. Today we'll present to us the title High Voltage Synchronous Rectification Design Consideration to Dr. Oscar. Oscar, can you share your screen right now?
Sure.
And start your presentation.
A bit about my background, I think was previously mentioned. I did my bachelor's at UT. I'm currently ABD, also dissertation under Dr. Lai at Virginia Tech. Previously worked at Texas Instruments, HP, San Diego National Labs. I currently work at Argo AI full-time. I work in the LiDAR Power Electronics Design Group. So I deal with the primarily design of resonant converters, wireless power transfer units, anything that we need for LiDAR sensors. Argo AI is a company. We do driving vehicle deployment, self-driving architecture. We are co-owned right now by Volkswagen and for the fleet of vehicles they have out in Pittsburgh. So it's at this point it's a multinational corporation all over. So on to the actual topic for today. So I'm going to give a brief background into high voltage power electronics and how it pertains to synchronous rectifiers, which is what my kind of contribution is into. Issues with high voltage SR, two main issues we'll be looking at. And I'll be following with my solution proposals and then the conclusion. So high voltage power electronics. So kind of coincidentally, I work in the automotive space now, so I see a lot of it. But traditionally, high voltage power electronics can be found in hybrid electric vehicles, traction systems, so trains, industrial, moving equipment, server systems, fast chargers. Tesla has a lot of high voltage power electronics development. And specifically for our lab at Virginia Tech, FEEC, we deal with a lot of utility applications, specifically things such as solid state transformers. So solid state transformers, or SSTs, are discrete power electronic systems combined for AC to AC power conversion. So at our lab, we build the AC to DC converter part, and there's a DC to DC and then a DC to AC. We build really the front end. Solid state transformers are very scalable, they're very high efficiency, and offer control through power line communication over traditional wire wound transformers. So these are being compared to traditional passive. On the side, we have the architecture for our AC to DC stage at the lab. So we have high voltage ACN, typically high voltage medium AC lines, so 7.2 kV or so, and then we have our low voltage high current DC output. So the way we achieve this is we have multiple modules in series to break up the voltages into smaller chunks, and then we have a diode followed by a DCX. The majority of my development comes specifically into that LLC DCX converter portion. So what is the LLC DCX? Well, traditionally, every sort of high voltage AC power electronic system needs isolation to protect itself from any sort of high voltage short or spike. So in our system, we build this isolation directly into the DC to DC circuit, specifically with the LLC DCX, which is a resonant circuit plus a transformer. So this is the typical LLC DCX circuit that we work with. It's comprised of three main components. First, the half bridge, that's the excitation source, the resonant tank, and the rectifier. So this is just a traditional resonant converter. So these are the key LLC DCX waveforms. I think this is relatively straightforward. We're operating right at the resonant point. So whenever we feed a square wave into the inverter, we get a pseudo-sinusoidal secondary side current, and we get a square wave secondary side voltage that is then rectified down into a DC or SR. This is the majority of my contribution. So what is it? So SR is very simple. We're replacing any sort of diode with a diode synchronous switch because the channel path of a MOSFET is much more efficient than suffering that forward drop loss through a diode. Control is primarily performed nowadays through drain source voltage sensing. This is the bulk of SR that you see in industry today. There are new methods such as volt-second balance sensing and a lot of open loop methods, which I'll touch on in the later slides. But drain source SR is the predominant method for SR. So how does drain source SR work? So on the right-hand side, we have the rectifier from the previous LLC DCX, but now we've taken the diodes out and placed in MOSFETs for both diodes and a traditional SR chip. Drain source voltage sensing physically senses the drain and source of the MOSFET. So we have the SR chip sensing the drain and source pins. So initially, the SR FET is off. Any sort of rectification is done through the body diode. So from T1 to T2, a little bit of current flows to the body diode, and the chip senses that forward drop, in this case, negative VF. From this point, the SR FET is turned on, and then you get the I times R drop across the SR. Eventually turns the system off, and the VDS drops below the turnoff threshold, and the diode catches that remaining current. This is the undesirable state, the parallel diode conduction state that we try to avoid. Now, if we compare all sorts of SR algorithms that are out today, we see one main issue. They're all relatively low voltage. The highest voltage that you can achieve with SR is with open loop SR, which is actually also done by our lab using fiber optics. And those are very expensive to scale, especially for larger systems. So drain source SR is about 200 volts. That's the manufacturer rating for the chip. And there's a lot of research into 12 volts. And then there's a lot of current sense methods, but those are also very complex. They require DSPs and a lot of high-speed logic. So nothing is very scalable, cheap, and easy to do. So this is the broad issue statement. There's closed loop high voltage SR. It does seem like a good platform to start with and is already very, very common. So the issue with the drain source SR is the chip limits the voltage. So the SR chip sensing the drain and source pin, we are limited by the IC designers and what can design whatever they're working with. And really this is the limiting thing. However, one key item to note is the switching moments for the drain source SR all happen at very low voltage. near or less than 0 volts. So technically, if we can block high voltage, we should be able to use this same method for kV levels, kilovolt levels of rectifier voltages. So there's 3 main areas necessary. Sensing issue, which I've touched on. There's a light load operation issue, which I'm not going to get in the presentation, but I've added a lot of citations on the last slide if people want to read into the paper. And then sensing accuracy, which I will touch on later on. So the high voltage sensing solution is actually remarkably simple. If we add a blocking FET directly in the drain source sense path for both the high and low side of that previous synchronous, the SR controller, whenever we bias the gate of the blocking FET to a fixed voltage source relative to the blocking FET source, relative to the SR synchronous rectifier MOSFET source, sorry. So in the next couple slides, I'll go over how this exactly works. So we're seeing the exact same system that we saw in the previous slide for drain source SR, but now we're including a blocking FET inside the drain pin. So the blocking FET is initially off and the SR FET is initially off. VDS across the SR FET can be modeled as a capacitor, and the capacitive divider of CSR, which is the capacitance inside the SR controller, it's a parasitic, and CP, the parasitic capacitance across the blocking FET, determine the voltage across VSR. So it's just a capacitive divider. So between T1 and T2, whenever the current first starts to flow, the blocking FET will turn on. In between T1 and T2 is this transition TA. TA is whenever the VDS hits the VCC minus VT moment. Let me see if I can get my laser pointer. This moment right here. So the blocking FET is off. ZVS is discharging the capacitance across the SR FET. VDS decreases. Across the VGS, VG2 and VS2 increases. And this causes the block on. The critical moment is this VCC minus VT moment, where VCC is the gate bias voltage and VT is the blocking FET threshold voltage, since that blocking FET does have some threshold voltage. From TA to T2, TA being that transition moment, the SR FET will remain off until that negative forward voltage is sensed again. From T3, drain source SR, we saw this in the previous slides. This is just normal SR control operation. So now the blocking FET is on, the SR FET is on, the SR controller is not affected by that blocking FET. Things work as normal. From T4 to T5, this is that early turn-off issue that we saw previously. The controller turns off early because there's a sensing parasitic that I'll mention later on. At T4, the I times R product drops below the internal SR controller turn-off threshold value, and the SR FET turns off. From T4 to T5, that big old body SR FET, an undesirable, but is just an unfortunate circumstance of drain source SR. From T6 to C7, another very critical moment happens. Now the blocking. So this happens at TB. Once again, we see that very, very critical moment, VCC minus VT, where that transition moment happens. So from T6 to TB, the blocking FET is on. The VDS will start to increase again because it's being charged by the transformer current. And the increase causes VS2, the sense or the source of the blocking FET, to increase, which will decrease the blocking FET source voltage and cause SR FET, cause the blocking FET to turn off. So from TB to T7, the SR is very confusing, especially if you're not familiar with drain source SR. But the takeaway is very simple. If we bias the gate of the blocking FET relative to the SR FET to some VCC voltage, the blocking FET is a completely passive hands-off solution. It can be modeled as a capacitor, some parasitic capacitance CSR. The blocking FET also has 2 states, on and off. So this creates 2 important equivalent SR circuits. First, when the blocking FET is on, which means the SR FET is off and there's a low VDS voltage, So in this case, the SR controller is sensing the SR FET. The blocking FET can be modeled as a resistive channel. When the blocking FET is off and the SR FET is off, which means it's blocking the SR controller from the high voltage across VDS, the blocking FET can be modeled as a capacitance, in this case, CP. What this tells us is the voltage that can be seen across the SR controller is a function of the capacitive divider of both the SR controller and the blocking FET. However, there's one very important condition that must be addressed: that initial threshold voltage across the blocking FET. So CSR is charged to an initial condition voltage, VSR initial, of VCC minus VT. Once again, we see that very important transition moment I was talking about, VCC minus VT, where VT is the threshold voltage of the blocking FET and VCC is that gate bias voltage. So once we have that figured out, you can derive a very simple equation to model what the voltage across the SR controller can be. The question is, what happens if the capacitive divider is still not enough in limiting VSR? There's one very simple solution. There's actually two, but I'm only going to go over one for time's sake. We can add one single diode that clamps the drain sense pin directly to VCC. This shunts any sort of current past the VCC into VCC and forces the remaining voltage across the VDS of the blocking FET. So this simplifies your design greatly. If your VCC is at 5 volts and your SR controller has a sense rating of 50 volts, if we add one diode right here, the voltage across the drain source sense pins will never exceed the VCC, which would be 5 volts. Next comes the verification. So this was our LLC DCX and Boost active front end that I previously mentioned from our SST at the lab. So we took this and we designed a new synchronous rectifier board with the Texas Instruments UCC 24610 and the onsemi NCP 4303 drain source SR controllers. So we have the high side circuit here, we have the low side circuit here, and the auxiliary power down here. The high side power is done through a bootstrap diode, so we're reusing the low side auxiliary power for that. And we can see the blocking FETs as shown here. So these are the specifications of the SR board. These are the specifications for the power stage. The blocking FET says it can be rated up to 600 volts, and we're only going to about 300 with this DCX setup. So let's see if it works. So the first thing to do is to validate the capacitive divider model with both SR controllers. So we're modeling both of these controllers as some parasitic capacitance. So the CSR is measured to be about 1 nano for the TI controller and 960 pico for the onsemi controller. And the parasitic capacitance across that 600 volt blocking FET to be around 36 pico. So based on the models with the same blocking FET, a 5 volt gate bias, the 24610, the TI chip, has a datasheet limit of 50 volts. We can boost that to 1,500 volts. And the onsemi chip from 200 volts to 5,500 volts without any sort of clamping or external CSR. So these design equations were validated only at 340 volts VDS. So it's very difficult to design any converter to even get to 1 kV. But just based off of preliminary analysis with what we have measured and our equations, everything matches pretty well. So this was the hard-to-find arm. This converter was designed by one of the other students in the lab. It's a 330 volt input, 1 kV output LLC DCX for another DOE project that we had. But what we can see is whenever we placed our blocking FET solution into the SR board that they used, we were able to successfully have proper SR operation at over 1 kV. I believe it was about 1.05 kV. In this case, we're using 1.2 kV blocking FET. So overall, we are what I believe the first lab to be able to achieve any sort of kV closed loop SR control. And this entire setup only costs, I think, a couple dollars. It's a very simple setup. We're using a commercial chip, just an off-the-shelf MOSFET, and those design equations that were derived. So this brings us into a second issue, an early turn-off issue. Now, this has always been a problem with drain source SR. At the end of the day, you are sensing the drain and source voltage across a MOSFET. You'll always be sensing some sort of parasitic as well, this LP. So anytime there's decreasing current through your rectifier, this will induce an opposing voltage to the resistive channel on your SR FET, which means the SR controller will shut off too early and force that parallel diode to conduct. So once again, that's undesirable, and that's not something that we want, but is inherent in drain source SR. This problem is even worse typically in high voltage situations because the current magnitude is very low, which means it's very difficult to sense that drain source I times R product whenever there's such low current. So this is a test example of that early turn off issue. Ideally, we want the gate signal to turn off at that zero crossing moment here and here, but the gate signal is being turned off much earlier. This is with the TI chip, the 24610. So what this means is this middle point in between, the body diode is conducting. So this results in very, very high body diode losses, and as you can imagine, quite a lot of conduction loss into the system. So there's two main rectifier architectures that need to be identified. So in high current rectifiers, there's a lot of paralleled switches. This is in order to increase the current handling capabilities of the rectifier. You'll see this a lot with VR and motherboards, anything with low voltage, high current. There's also another type of rectifier, which is what we use, which are single switch or intended for low current applications. For each of these rectifier architectures, we are proposing a separate method. The first is sequential parallel switching for the parallel switch rectifier, and then multi-level gate driving for single switch rectifiers. So for the single switch rectifier, which what we have on our LLC DCX, we're proposing an adaptive multi-level gate driver. So previous research, because this is a very old problem when it comes to drain source SR, has proposed very complex compensation networks tuned specifically to that parasitic inductance in the sensing path. Proportional gate drivers, things of that nature. They typically require a lot of additional components or even more external switches from 1 to 2 in order to make that perfect turnoff happen. So that's undesirable. It's very complex. Let's see if we can find a simpler method. So we are proposing, or I'm proposing, a multi-level gate driver that reduces the gate voltage across your SR MOSFET once you're close to that turn-off moment. The idea is simple. For a given RDS on and a given parasitic inside that sensing loop, you get a certain phase shift in the signal. This phase shift is ideally 0 if there is no parasitic. However, there is a parasitic, so your phase shift, is something in the order of anywhere from 5 to 20 degrees or so. If we increase the RDS on near the turn-off moment for the same given parasitic, we can decrease that phase shift. So we can get a more accurate turn-off moment if we increase the RDS on near that turn-off moment. So this is how it would look like in practice. We would have initial turn on, and somewhere along the way, we would reduce the gate voltage. This is the VGS signal going to the SR FET prior to the turn off moment. This would push out the total SR conduction time and reduce this diode conduction time. The hard part is timing when this transition moment will happen, when you start dropping down the VGS. With a fixed frequency setup, it's relatively predictable, but this transition moment is incredibly important. You can see here this transition duty cycle. 0 would mean a transition point right at the beginning. We want to minimize the amount of low VGS because this increases the channel conduction loss because RDS goes on, but we want to time it to be right before the falling edge moment. So the farther along we go, 40% transition duty cycle, you can see how much conduction loss is reduced. So we can reduce it almost by over half at this point, about 3 times, over 3 times as well. The higher and higher we go, but timing that is the critical part. This also increases the load range. So at light load conditions, the SR duty cycle is very susceptible to perturbations. As previously mentioned, we are sensing the voltage across the drain and source sense pins through a resistor, the RDS on. So there's very low current, there's very low voltage magnitude as well. The I times R product is very, very low. So you get very large duty cycle jumps that can cause an internal current oscillation phenomenon. I've published a couple papers off this that are in the very last slide that I'll point to, but I don't really touch on this too much because it's kind of a complex problem in itself. So multi-level gate driving actually stabilizes this issue because it increases the voltage magnitude that the SR chip is sensing. By decreasing the gate source voltage, we increase the RDS on. Because we increase the RDS on, the I times R product is also higher. So we push away that light load condition. So this is how we verified the multi-level gate driver. First, we had to actually build the multi-level gate driver. So this was done with 2 discrete power supplies, an isolated half bridge, and a digital adaptive delay that was done through an FPGA. So the SR controller will send the control signal and the rising edge through some sort of isolator, some sort of signal isolator into the FPGA. The FPGA will then post-process that signal, and after a certain amount of time from the rising edge, send it back through that isolator into the block diagram, but it gives you some idea of how it was implemented. So I'm using a Spartan 6 FPGA, so it was all done in Verilog, and it's programmed to be adaptive, so that transition point actually sweeps across over time. So VDD1 is 8 volts, and VDD2 is 10. So with both power supplies on, I'm giving 18 volts to the SR FET, which is back here, driven by this TI gate driver, the UCC 27531. Whenever the adaptive multi-level gate driver transitions, it goes from 18 volts just to 10, just to VDD2. So here are some actual verification waveforms of that adaptive multi-level driver in use. So first, we have the secondary side current up here in gold. We have the VGS, SR MOSFET, and we have the VSR, the signal coming from the SR chip. So A first shows traditional 2-level turnoff. So without multi-level gate driving, we can see that falling edge is very far away from the 0 crossing moment. This is bad. That means everything from this falling edge to the 0 crossing moment is all being rectified through the parallel body. By reducing the gate voltage at some point, we can increase the RDS on. As you can see, we become much closer to that ideal 0 crossing moment. Unfortunately, all this time right here is spent at a lower RD or at a higher RDS on state. So the conduction loss is very the optimization process. You can see that edge has been slowly pushed out. We lost experienced. So the duty cycle is extended a lot, from 29% over here to 43%. At a 12.5% transition duty cycle, which is what this is, the losses can be reduced by over 57% once we push it out near the edge, with an additional 66% loss reduction possible with more tuning. This was the second solution, a sequential parallel switching for the parallel switch rectifier. So traditional parallel switch rectifier uses batch turnoff. That means all the MOSFETs turn on at the same time and they all turn off at the same time as well. What we're proposing for those high current parallel switch rectifiers is something called sequential parallel turnoff. In simple terms, we are turning the MOSFETs off one group at a time. This is to achieve the exact same end result as the multi-level gate driving. We're trying to increase the RDS on near the turn-off moment in order to push out the SR duty cycle. So once again, previous research has proposed a lot of different compensation networks. All of that is very difficult, and from the application side, from the end user side, nobody actually does that. So this proposed method is actually relatively passive. That only requires different turn-off threshold voltage changes on the SR chip. So sequential parallel switching, SPS, sequentially turns off parallel SR FETs instead of batch turn off. So sequentially just means one by one. So by turning off one switch before the other, the effective RDS on can be boosted. So what we can see here on this right-hand waveform is by turning off one FET before the other, we can increase that VDS magnitude just slightly enough to push out that turn-off moment. This is actually for the same turn-off threshold, since we weren't actually able to get this idea down into a chip. So we use this with minimum on-time blanking. So this results in the same increased performance that we saw with multi-level gate driving, except with less changes necessary. This is something that most chip manufacturers can integrate onto their SR chips. So this was our test board. So once again, we used the same setup. This was actually sponsored by TI at the time. So we're using TI GAN boards, which are not great rectifier devices, but still work for proving the concept. So we're using 3 TI GAN LMG 3410 EVM modules in parallel. We're using 2 TI chips, the same chips that we're using in all the previous research. And the idea is we're going to turn off 2 modules before we turn off the last module to implement this sequential parallel switching. So these 2 will turn off first, and this one will turn off last. And what we can see is we can almost double the total SR conduction time whenever we do this SPS. So simulations show about a 20.8% loss reduction over batch turnoff, and a 51% loss reduction is achieved over third quadrant conduction. Now this will vary depending on how lossy your parallel rectifier diodes are. In this case, it's just third quadrant conduction, but the concept is still proved. So further simulations were run to quantify this method if we were to use it with threshold tuning instead. So if we turned off one set at -5 millivolts threshold voltage and one at 0 millivolts. As we can see, the majority of the loss reduction happens at light loads, whenever there's low drain source voltage signal. And as we get to higher and higher power, the contributions starts to decrease. So in conclusion, today I've at least hopefully shown you guys a brief idea of what high voltage SR looks like and how it can be implemented for a very low cost. And this is a method that we have shown to be working at over 1 kV. And with those high voltage, with this high voltage setup comes new challenges, specifically in drain source voltage sensing accuracy. So 2 other methods of improving this accuracy: SPS, sequential parallel switching, and MLGD, multi-level gate driving, are identified, analyzed, and validated. These are the publications. I'll leave this on there if people are curious to see some of the low current oscillation issues or anything else. And I think that's it for me. Thank you for your time. Any questions?
Thank you very much, Oscar. Very nice presentation. You have an overview about the Synchronous rectification and many solutions shared to us. We have the first questions from Mr. Hong. So, Oscar, can you open the Zoom chat and can you reply on the question?
Oh, I see it now. Yes.
There are 2 questions. The first one, have you ever missed the corona charge effects while the voltage ranging on some switching nodes inside the circuits?
I'm not sure. I'm not sure about the corona discharge. I'm not familiar with it. If they do see it in our circuit, it's probably there, but I'm personally not familiar with the corona discharge effect.
Okay, and let's move to the second question.
Sure. The very first page is feedback volt. Do we have any considerations on high output voltage feedback tolerance? Any accuracy requirements differ from low voltage feedback? That's a good question. Let's see, very first pages.
The first page of the feedback voltage. Do you have any consider on the high output voltage feedback tolerance, any accuracy on the requirement difference, low voltage. I think Mr. Hong, you can directly add the question. You can turn on.
Hello, Mr. Oscar. Microphone clear. Okay. May I ask for the requirement about the percentage of voltage tolerance of the output voltage feedback tolerance about 10% or about 1% or maybe could you be more specific on the tolerance?
Sure. You're talking about the tolerance for the full system or just the synchronous rectifier?
I mean the output voltage feedback system, voltage feedback feedback tolerance, the output voltage.
Oh, I see. Okay, so of the DCX, I see what you're saying.
Yes,
I think you're this output voltage, correct?
Yes, the V out.
Yeah, of V out. For our system, it's actually pretty. I think it's less than 5%. It's pretty. It's pretty
5%?
pretty good. Yeah. It's actually regulated. Let me see if I had that slide down here with the test. So we have an active front end. It's a PFC boost, so it is actually regulated. And the front, it's a fixed step down.
Okay, I mean the output voltage. You mean that 5% is you have any consideration?
Oh, I see. We were given a spec. From what I recall, we were given a spec. So this was not something that we chose or designed for.
Okay, so more question. Thanks.
Sure. Anyone else?
Okay. Another question comes from Dr. G. Can you switch your phone and make that directly question?
Okay, thank you, Mr. Chairman, and thank you very much, Dr. Oscar, for a very nice presentation about RSC. Below. Firstly, can you hear me, Dr. Oscar?
Yes, I can hear you.
Okay, I'm Win from Japan. I have a couple of questions. Firstly, based on your current figure, I think that is the operation rate, operate your technique over resonance, both over and below resonance.
We have, yeah. The tuning was not done for me. You know, the majority of my circuit is adapted onto the DC. But yes, we've tested this slightly below and above resonance. The controller purely operates off of the sense to voltage across the drain source sense pins. So let me go back up here.
So you mean there is no problem if you operate under or below, below or over resonance? Right?
It's I believe right now they're operating slightly over resonance, and that's not a problem. The 301 kV converter, near resonance, but from what I recall, they're not having any problems.
Okay, thank you very much. The next question is regarding your auxiliary circuit. I saw that you have a couple of MOSFET and diode and capacitors. My question is, what is the specification of the auxiliary circuit, like etc.? Because I think this auxiliary MOSFET must be much more faster than the main MOSFET, right?
Oh, I see. The auxiliary MOSFET, you mean the blocking FET, correct?
Yes,
This
yes,
FET.
yes.
Yes.
I suppose
Yeah.
it must be much faster, but the voltage you show in the slide is 1 kV. I
Yes.
just confuse the very fast MOSFET with very high voltage, which is maybe very expensive and difficult to choose, right?
I see what you're saying. Yeah, so it's actually not that fast. We're switching this converter quite slow. I believe this one is about 300 kilohertz. But the transition times that you're mentioning about, so the actual physical MOSFET is quite small. So the RDS on is actually quite high for this blocking FET. I believe this FET is only $1 or $2. It's actually very cheap. Because the RDS on is not a primary concern of ours, as long as the gate charge and everything is quite small, all we're really caring about is the parallel CDS, which I think, as I mentioned, the voltage across the SR controller is a function of the CDS. So that's our main concern. But no, these MOSFETs are all very cheap, a couple dollars. I think some are even 50 cents.
Oh, okay, that is reasonable, I think. Okay, may I move to the next question?
Sure, sure.
Okay. Regarding your technique, I think the objective is to increase the effective duty cycle to reduce the diode conduction period, right? Can you confirm that?
The the blocking FET is to increase the voltage range that we can use at SR, but the other techniques that I discussed down here, the SPS and the multi-level gate driving, those are used to increase the duty cycle. Yes.
Okay, so that is about the second part of your presentation.
Yes.
The question is, you try to reduce the gate driver voltage to
Yes.
increase the drain source resistance, right?
Yes.
My question is, you have to pay a lot of effort into changing the voltage level. You use some switch to change the level. Then I
Yes.
think the speed of the switch you use also it affect the loss. I mean the switching loss of the auxiliary switch, and maybe I think in this part you may have to trade off between the additional loss of the auxiliary uh, circuit. I mean to change the level and the loss you can save by extending the duty cycle. So have you considered that?
Yes, I think I see what you're saying. So if I understand the question correctly, you're saying there is a trade-off that must be made between the multi-level gate driver loss from the
Yes.
additional switches and driving circuitry versus the amount of energy saved from that parallel conduction.
Yes, that is what I mean.
Yes, that's in our case, it's not much of a problem since um, the secondary side rectifier switches we were using were silicon carbide. So the body diode is very, very lossy. So for us, we had a very, very large margin. It just made sense. But you are correct. For a traditional, maybe silicon system or something that does not have a very lossy parallel body diode conduction, it would be much harder to justify. Yes, you are correct. We're really hoping under these circumstances, all of this was done for a TI sponsored project, that they can take some of these ideas and integrate it into their SR controllers. It's obviously less lossy if they integrate it at the IC level than if we were to do it from a discrete perspective.
Okay. Okay. My last question.
Sure.
So your objective is to increase the duty cycle and to reduce the diode conduction interval. So do you have any result to show how efficiency can improve after applying your technique? I cannot see any like percent or efficiency result in your slide.
Sure. Yeah. Let me see. This one, it's kind of spread out, but this one was focusing specifically on the transition duty cycle. This was modeled off of I don't think I listed it here, but it's from the previous slides. It's off of a SCT 3017. It's a ROM. So excuse me, silicon carbide MOSFET cycle duty loss versus conduction loss. I think I have efficiency numbers for it. It's not in the slide though. Those were done with simulations as well. Let me see. Yeah, so these were simulated with the TI GaN EVMs, but compared with batch turnoff, we were getting about 20% loss reduction. And obviously another solution is, well, let's just turn off SR completely at light load. And if we were using SR over third quadrant conduction, we'd get over 50%. But if we were turning everything off with traditional batch turnoff, it'd be only 20%.
So overall, how much of the maximum efficiency you can achieve? Like more than 99 or?
For the total LC converter?
Yes, from the output to input to the output. How much of the maximum?
99, 98.9 or 99.
Wow, this.
But this
high.
one, but this converter was a very high voltage system. So, you know, it's not going to show the losses that well. I think with a diode rectifier, they were pretty close to 90.
Actually, I can read some articles show even if with only diode or a single traditional SR,
right,
they can
right,
achieve about 99 or a little bit more than 99, or like 99.5, 99.6 something from your application.
Yeah, no, for us, this is actually a very common question. You know, why have SR at all for a high voltage converter? Because the voltage drop across the diode is
very large,
insignificant when you're at 600 volts. This is actually a problem once you start scaling. Heat is an issue. The majority of solid state transformers are not cooled. Apply that by 50 or 60, depending on how many modules you have. The whole system, you know, in a big oil bath or something like a traditional transformer and placed somewhere without cooling. So SR is implemented at these conditions purely to reduce heat loss.
Okay, that's all of my questions. Thank you very much again.
Sure,
okay,
thank you.
Thank you, Dr. Jiden from Japan. And we have a couple questions from the Thang from Seoul in Korea. So please identify yourself and make the question. Thang?
Yes, hello, Dr. Oscar. Could you hear my voice?
Hey, I can hear you. Nice to meet you.
Yes, I'm Thang from Seoul in Korea, and my question is in the first in the near first page you mentioned about the LLC DCX, and actually the LLC DCX look like this type converter is for isolated converter and then fixed frequency, right?
Yes.
And then, but why? Because LLC has some problem because of the voltage gain is very sensitive with some tolerance of some device, like the capacitor is about maybe about 5 or 10% of tolerance values, or inductor is also have some tolerance. But as we know, as I know, there are another type converter is SRC. That means series resonant converter. That's not LC. The SRC, the LM is very high. LM value is very high. So in this type of converter, the tolerance of the capacitor and inductor is. So can you explain why we using the LLC converter for the DC application? The first question that.
Sure. Well, I can try. So I was not the original designer of this circuit. I was just designer of the attempt to design a high voltage SR circuit for it. So I'm not entirely sure, you know, why they chose a LLC over an SRC. But in our case, I think you can see our magnetizing inductance is actually also very high when compared to the resonant inductance. So the voltage gain has never really been much of a problem for us, especially at fixed frequency.
Yes, I see. It look like the almost SRC is as I mentioned.
Yeah.
Yeah.
So for the, if you look at some of the other like papers I've written over the oscillation issue, we treat it like an SRC model because of how big it is.
Yeah. Yes, thank you. Second question is related to in your proposals, gate driver, synchronous gate driver, you deal with some very high voltage application. Is as I hearing, actually I'm not in this type field, but actually I want to know what is problem when we deal with very high voltage application like that. Firstly, I hearing yours, your mention is about the voltage drop. In my case, I also do with some high voltage, very high voltage, around 1,800 kilovolt. But we have some problem is in the crosstalk problem. Did you hear about that? And this your in your proposals gate driver that also can deal with some problem like that, like crosstalk or another. Could you give me some keyword?
Oh, I see. You're saying, so crosstalk at high voltages, correct?
Yeah.
Right. We didn't see much of a crosstalk issue, but we had pretty good layout in the majority of our circuits, and everything was prototyped. Yeah, I don't have a good answer for that just because we didn't see any of the crosstalk issues. The majority of these converters that we're running at are pretty low frequency. The one I prototyped on, the high voltage one in particular, was only running at 84K. So we didn't come across many crosstalk issues.
Yes, okay, thank you. Yeah, that's all my question. Thank you so much.
Sure.
Okay, thank you. Next question from Anh Dũng. So please.
Okay. Thanks a lot for your nice presentation, and you give a very useful information about the SR driving and also the multi-level gate driving techniques. And firstly, I would like to share some information about the question like the Tang from Silicon Tech writes about why people they usually use the LLC, because LLC converter like the ZVS condition for all the MOSFET is independent on the output power. So it's for the SRC converter, like they are highly depends on the output power. So it's quite hard to design. Actually, it's quite hard to design the resonant tank to meet the ZVS requirement for all the power range. So that's why usually people they usually use the LLC converter. And also I would like to write some questions for you. Like, can you move to page 30?
Sure.
Yeah. So on page 30, actually you use the blocking mode, the blocking FET to share the voltage stress on the SRM IC and the FET. So it highly depends on the output
the CP,
parasitic capacitance of in FET, right? And yeah, and like based on the FOM, the fee is small, so the RDS will be high. So we have to choose the very small parasitic capacitance MOSFET. So RDS is high, so it will affect to the overall performance of the circuit or not.
Yeah, so I see what you're saying. Yeah, in our case, the RDS on is not too critical of an issue, since once again, whenever the SR FET is on, so let's go back to this slide. Whenever the SR FET is on, the voltage sensed across here, which is kind of, I think, in the microamps or milliamps, it's very, very small, but the RDS on just does not greatly affect the turn on or the turn off. So it's not something I've directly looked at. It's a good question that one could look into, but a negligible issue, if you will.
Okay, so and the second question is about the you can add more capacitor for the SR IC to reduce the voltage rest on the SR. So when you add more capacitor like this, the CSR is bigger, so it will be slower because of the charging and discharging time longer or not?
Yeah, so this was actually something that I think I cut out right before I sent the slides to you. But what En Young is saying is another method to reduce the voltage across the SR controller is to add external capacitance. Let's see if I can, not a pen. To add external capacitance to the drain source sense pins, so somewhere out here. And because you're increasing the capacitance across the controller, you're decreasing the voltage. Yes, in that case, the RDS on will matter a lot. So technically, whenever this is on, this does form an kind of an RC filter, if you will. So there are transient characteristics to it. With the parasitics in the SR controller, the inherent parasitics, which are only about 1 nano that we saw, the RDS-ons that you get will not greatly affect the controller performance until you're at very, very high switching frequency. But if you were to increase the external CSR to reduce voltage and not use the diode clamping method that I've shown in the previous slides, yes, you will start to see a delayed turn on and turn off, since this resistive channel will start to limit the current if you add a very, very large external capacitor.
Okay, so but usually for the SRIC, for the commercial SRIC, the maximum switching frequency can go up to 1 megahertz. So usually will it affect on the performance, because below 1 megahertz, will it affect the performance or not?
It will technically affect it all around. So we have actually tested this method to 1 megahertz. The 1 kV test we also ran at 1 megahertz just to see how it would perform. And there is a very, very noticeable difference if we add, say, a 100 nanofarad capacitor across the SR controller. We lose, I think, in that case, almost 25% of duty cycle. The turn on was very delayed and the turn off was very delayed. Since during turn off, we have to discharge this cap. So if we add a very big cap, it takes a very long time to discharge and it takes a very long time to charge. The discharging is a lot worse as well, because late turn off means turning off after the zero crossing. So that could cause a shoot through issue. Yeah, so the external capacitance needs to be very, very carefully selected. But En Young is correct. At higher frequencies, you do not want to add any sort of external capacitance. The diode clamp is much more preferred. And at very, very high frequencies, multiple megahertz, the inherent SR controller capacitance will become an issue, regardless of what RDS on you pick, since they'll all be pretty high at that point. So that's also a very good topic someone could explore.
Yeah, and I feel this one is a very good technique for the future device. In the future, they can develop some very good device, and you can do work with a very high frequency. So my last question is about the multi-level gate driving, and you create two voltage level for the gate signal.
Yes.
So when you change from the high voltage level to the low voltage level, so will it affect how so that when you change from 18 volt to 10 volt like this, so will it create the undershoot in the VGS, and then it will make the MOSFET turn off suddenly or not?
We never saw that issue. Let me get to the waveforms. We never saw the undershoot issue, but that's because we had two discrete isolated power supplies. We had one at 8 volts and one at 10. We were not draining the CGS off until 10 volts. We were forcing the CGS to a fixed voltage at 10 with the half bridge. So we never saw the undershoot issue, but potentially that could be an issue.
Okay, thanks a lot for your presentation. Sure, thank you.
Okay, thank you. So I had just a small question on your topology, and because you work with the high output voltage around 1 kilovolt, so are there any solution like multi-level rectifier? Why you don't consider on this?
What do you mean by multi-level rectifier?
Multi-level, that's the multi-level, you can make the separate the level.
Okay, we mean that the second side we use multi-level.
Why did not? Oh, I see what you're saying. As in why we did not use multi-level gate driving for this design as well? Yeah, I'm not sure what you mean by multi-level configuration.
It should be the power stage. Yeah.
Yeah, to review the voltage rating on the switch.
Oh, I see. You're wondering why the output voltage is so high?
No, because I know so far we also had for the high voltage solution, we usually use the multi-level topology, and that's look like a multi-level rectifier. We had the outputs very high voltage, but we use the multiple level voltage. That means you can use the low voltage rating of the FET.
Oh, I see. Yeah, I think I see where the confusion is coming from. So this is not the same DC to AC portion. So we wanted to step it up. So we're converting in this DCX a relatively low input voltage from some bus 330 to 1 kV. And this circuit back here is actually an unfolding stage for it to be converted back to AC. So we wanted the high voltage. We're not using a multi-level in this case because this was a new topology that was proposed that we were being funded for. But of course, there might be a case to use a different multi-level converter for that step up, but I'm not too sure. I did not design that portion of it.
Okay, thank you very much. So right now we have the time.
Hi, Dr. Kai.
Yeah.
It's Tom here. So I have a very quick question regarding the presentation.
Sure.
So hi, Mr. Oscar. Thank you for presenting such an interesting topic. So I have a quick question here. So you present the multi-level SR gate drive so basically you try to reduce the RDS on, right? To reduce the conduction time of the diode, the body diode to increase the efficiency, right?
Yes.
So, okay, so I see from your circuit, you have the adaptive, digitally adaptive delay. So my question is that how you know exactly the value of the RDS on to control that time?
Sure. So right now we're running an open loop. The FPGA does not actually know what the RDS on is. All the FPGA is focused on is trying to get the falling edge as close to the SR falling edge as possible. So we're trying to get this transition point as close to the falling edge as possible. So it's actually, what I had implemented was it was just kind of an open loop sweep, and then it would arbitrarily look at how much noise is present on the circuit and try to get it as close to it as possible. But yeah, it's the actual VDD selection and the FPGA are completely separate. It does not know what the RDS on is.
Okay, because I see that, you know, in the actual application, when you run the circuit at pretty high temperature, you know, the RDS on, you know, varied a lot with the temperature increasement, right?
Right.
So
right.
Yeah, so it's pretty difficult to, like, you know, have an online estimation of the RDS to have a exact control of the RDS on, I think.
Right. Yeah,
So,
that would definitely be a very interesting topic if you could actually feedback some sort of RDS on value or RDS on, you know, or calculate it even based off of the conduction time. That would also be possible in the FPGA because we already are detecting the rising and falling edge. So we could, based off of the current level and, you know, known factors, determine that. But yeah, that's also something that could be explored.
yeah, I think, like, you know, in the actual about MOSFET, they always have some kind of RTD resistance. So from the RTD resistance, you can consider that feedback information of the voltage. so you can know exactly the value of the K temperature. And then from that, you can determine exactly the value of the RDS on, depend on your operation condition.
Right, I agree. Yeah, that's definitely a very deep topic that could be explored.